The matrix to solve the system, we're going to start by writing the augmented matrix that corresponds to this system. And from here we have a couple different techniques, but they both start off the same way. When we get to a certain point, then we'll have to decide which technique we want to use. And the way that we need to start is we need to get ones down this main diagonal of the matrix. So we want all these entries to be 1. And we want the entries below them to be zeros. So we want zeros in these three spots here. So we'll start with the first column, get a 1 in the upper left and zeros below it. Then we'll move to the second column, and then finally the third column. So to get a 1 in the upper left, I'm simply going to just switch rows 1 and 2. Just interchange those two rows. Okay, and I've indicated that operation that we're using to get from one matrix to the next there. So now I want to focus on getting zeros below that 1 in these two spots here. So to get a 0 where that 2 is, I'm going to multiply row 1 by -2 and then add it to row 2. So that would make it so I have -2 times 1, that's -2, plus 2 would give me the 0 that I want. Now I have to do that in each column in the entire row, but that'll obtain the 0 in that place. So we're going to do -2 times row 1 plus row 2. That will become our new row 2. And the same step, we want to get a 0 in that lower left corner. So I'm going to multiply row 1 by -1 and add it to row 3. And that will become our new row 3. Next, if I notice that every entry in that bottom row is a multiple of 3, I can, in a sense, reduce that bottom row by just multiplying row 3 by 1/3, which would be the same as dividing each entry by 3. Since our next goal is to have a 1 here where this 3 is and a 0 below it, I see that I can accomplish getting the 1 in that spot by switching row 2 and row 3. So we'll go ahead and switch those two rows. And now to get a 0 below that where that 3 is, we're going to multiply row 2 by -3, so that when we add it to the 3 we get 0. So we're going to do -3 times row 2 plus row 3, and that'll give us our new row 3. And by completing that operation, it also gave us a 1 there in that bottom right corner of the diagonal. So that accomplishes those goals I set out at the beginning. So we, depending on which method we're going to use, we would either stop here and go back to a system of equations, or we would continue with the matrix. So stopping here and going back to the system is called Gaussian elimination with back substitution. At this point I would rewrite the corresponding system of equations, so I'd introduce my variables back in there. My first row says x minus y plus 2z equals 9. Second row says y minus z equals -1. The third row says z equals 3. So that essentially gives me my solution for the z coordinate. Now I can plug that back in the equation above where I have y minus z equals -1. Do y minus 3, because z equals 3, equals -1, and then solve for y. And then take those two values and plug them back into that first equation to solve for x. If we continue with the matrix, that's called Gauss-Jordan Elimination. In that case, I would try to get zeros in these three places. And that way my first row would just tell me 1x, or x equals whatever number is over here, and then y equals whatever number is here to go along with the z equals 3. So if I continue with the matrix, my solution is essentially there in that last column. So I'm going to go ahead and continue with the matrix. So to get a 0 here where the -1 is, I'm going to add row 3 to row 2, and that'll give me my new row 2. To get a 0 where the 2 is, I need to do -2 times row 3 plus row 1 to get my new row 1. And then to get a 0 where that -1 is, I want to add row 2 to row 1, and that'll give us a new row 1. So now we get our top row as an equation says 1x, or x equals 5, so that's our x coordinate of the solution. Our second row says y equals 2, and our third row says z equals 3. So you want to plug that back into all three original equations and make sure that it works.